So in this lecture we are going to study, in this new lecture series we are going to study electrodynamics, and we will first understand what electrodynamics hopes to solve, or what we are trying to understand from the system when we study electrodynamics. So as you can see, the dynamics part mean the motion. So dynamics part is concerned with the motion. So when we study about electrodynamics, we are basically interested in finding the dynamics or the motion of the particle under some influence of a force. So first I will tell you what we try to solve, or what we try to understand, what we hope to understand from the electrodynamics. So suppose that I have a test charge small, I have a source charge Q, source charge. So I have a source charge Q and a capital Q, that is the test charge. Okay, so I have these two charges, Q, that is the source charge, that will be some source of field that will act on Q and will influence the Q. So and the capital Q is the test charge which will feel the field or the influence of the source charge Q. So if I draw a coordinate system, so if this is my x, y and z, and the position vector of the source charge is rq, and the position vector of the test charge is capital Q. So this is the position vector of the test charge and the source charge, and what we are trying to understand or trying to solve in the electrodynamics is that under the influence of the source charge, what is the dynamics of this test charge? So in electrodynamics, we are trying to solve what is the dynamics or motion. So what is the dynamics or motion of the test charge capital Q under the influence of source charge? Okay, so that's what we want to find, or we want to calculate the trajectory or the motion of the test charge Q under the influence of source charge. So the source charge will create some kind of field that will act upon Q and will provide a force to the particle capital Q that will that will make the capital Q test charge in motion. So and in general or in realistic scenario, these position vectors are dependent on time. So and if this is my separation vector r, so this is my separation vector, that is the distance, the vector between source charge and the test charge, and this separation vector also depends on time. If my rq is an rq depend on time, so this also depends on time. So if I have a formula that tries to compute the interaction or the force between test charge and the source charge, so if I have that formula that will tell us the force between test charge and the source charge, so you'll be surprised that that force would depend on the velocity, acceleration, and the separation distance of the test charge. So when we try to study electrodynamics in realistic scenario, so then my force will depend on the and acceleration, and the separation vector. So So that's why it's a very complicated thing to solve. So if my source charger and test charger are moving, then my force would depend on these all physical quantities. So that's why we need to reduce our problem to a more easy problem. First, we will try to understand a more easy problem or a more easy picture. So that's why we first introduce or first study electrostatics. So in electrostatics, we put a restriction that my restriction is that my source charge or charges should be static. So that means the position vector of the source charge or source charges or system of charges that will influence the test charge should be fixed. Its position should not change with time. So that's the restriction we put on the source charge, and it's more easier to understand electro. It's then easy to understand the dynamics of the test charge. So in general, my test charge is in motion, but my source charge or source charges will be at rest. So that's why we first study electrostatics, because the general problem is very difficult to solve or to understand. That's why we shift to electrostatics, in which we put a restriction that my source charges should be fixed. But in the electrodynamics or in the real world or in the real scenario, my source charges position or source charge or source charges position are changing with time. But in electrostatic, my source charges should be static. That is, its position vector should not change with time. My my test charge position can change, and it will change because due to the influence that due to the influence of the source charges, a force will act on Q, capital Q, that will that will cause the test charge to move. So my position vector of test charge can change, but position vector of source charge should not change. Okay, so this is electrostatics, and we will first start our discussion by studying electrostatics. And so I'll rub this down and write it again. So we will first try to understand electrostatics. So in electrostatics, I have a source charge small q and a test charge capital Q. And these are the respective position vector of the test charge and the source charge. So this is my source charge. So source charge meaning will be cleared when I'll come to electric field and other things. So this is test charge. Okay. So this small q is my source charge and capital Q is test charge. And my RQ vector minus RQ vector is equal to R. That is the separation vector from source charge to the test charge. Okay, this is the separation vector. Separation vector. So when we study electrostatics, what we have put up a restriction that my source charge or charges position should be, so my source charge's position should be fixed. That is, the source charge should be static. Okay, so this is my restriction, and what we now what we will now study is the formula that will give us the interaction between the test charge and the source charge. So we will first study Coulomb's law. Okay, so according to Coulomb's law, the force between source charge small q and the test charge capital Q. So I have a source charge and a test charge. Okay, and according to Coulomb's law, the force between the source charge and the test charge capital Q. So force, the magnitude of that force depends on the product of the test charge and source charge. Okay, and inversely proportional to the square of the separation vector. So this I have put up a mod. So mod means I have taken the magnitude of this separation vector and I have squared it. So my force depend on inversely on the square of the separation vector magnitude. Okay. So if I take a constant of proportionality to be small k, and I can write this down as q into capital Q upon r vector mod square, and this small r vector is the separation distance magnitude square between the source charge and the test charge. So r vector mod is the separation vector magnitude. Okay, so this is my formula for calculating the force between the test charge and source charge, and it's in general valid for any two charges. So if I have any charge q1 and q2, then my force will be F is equal to k into q1 q2 by the distance by upon the distance squared, that is the distance between these two charges. So, and in general, k, the small k is equal to 1 by 4 pi epsilon naught, and epsilon naught is permittivity of free space. So that means we are considering that we have put up our source charge and a test charge in vacuum. So this value of epsilon naught will change if I put my source charge and test charge in any other medium. So if I put my test charge and the source charge in water, then I have to use the epsilon value for that medium. For that is for the water. Okay, this is equal to permittivity of free space, and the value of small k is 9 into 10 to the power 9, and I have to, and the unit of this proportionality constant is Newton meter square upon c minus 2, that is Coulomb inverse square. So this is the unit of k, Okay, so that's how we calculate the force between any two charges. So if I have a source charge small q and a test charge capital Q, so this subscript S stand for the source charge and T stand for the test charge. And if these are the respective unit, if these are the respective vector, position vector for the source charge and the test charge, so this is RS and this is RQ and this is R vector. So this is the separation vector between the charges. So my F vector, that is the force, magnitude of the force between these two charges, is given by this formula, and the direction of the force is along this separation vector. So my F vector will be equal to 1 by 4 pi epsilon naught Q into capital Q by R vector mod square into R cap. And R cap, so I'll write it down over here. R cap is the unit vector along the separation vector. Okay, so R cap is the unit vector along the separation vector, and separation vector is the vector that vector between the source charge and the test charge. So my force is given by this. So the formula for the force is, this is the magnitude of the force, okay, and this is the direction of the force, and the direction is along the separation vector. So this completes our discussion on Coulomb's law, and now we will study about superposition principle. So in a real scenario or in general, uh, there can be a lot of source charges. So suppose that if I have a system of charges q1, q2, and this is the position vector r1, r2, and similarly I have another charge q3, and suppose that there are a lot of charges, so q4, q5, and goes to qn, and these are the respective position vector. So all these system of charges are my source charge, and I have a test charge capital Q, and I want to calculate the force on the test charge capital Q due to the system of charges. So to find the force on the test charge capital Q due to this system of charges, what we have to do is we have to apply superposition principle. So superposition is simply just vector law of addition. So as we know that force is a vector quantity, and to calculate the force F, that is force on Q due to system of charges, what I have to do is I have to consider each and every charge, and I have to calculate the force on the capital Q charge due to that small charge qi. So what I have to do is, suppose that if I try to calculate the interaction between q1 and capital Q, then that force will be equal to q1 capital Q. So F1 capital Q is force on the test charge capital Q due to 1, that is Q1. Similarly, F2Q is force on the test charge capital Q due to Q2. Similarly, F3Q is force on the test charge capital Q due to Q3, that is small q3, and these all system of charges are my source charges, and they will influence the capital Q or the test charge, and due to that influence or interaction, the Q or the capital Q test charge will move or will be in motion. Okay, so it will go up to Fi Fn Q. So this is force on the capital Q test charge due to the source charge Qn, and these all are my system of charges. So my formula changed to I is equal to 1 to n f f I q. Okay, so what I need to do is I have to just calculate this vector sum of all these forces, and then I can evaluate the force on the test charge capital Q due to all these system of charges. So we'll do problem on this, and it will give you a better understanding that how do we have to solve this problem. Okay, so to conclude that if you want to find out the force between the test charge and the system of charges q1 q2 q3 to qn, what you have to just do is you have to calculate the interaction or the force between the individual charge and the test charge, and you have to take a vector sum. Okay, so see you in the next lecture.